Continuing our discussion on the special purpose control charts, we have already referred to modified control chart, if you recollect, and what we have mentioned that the modified control chart is to be used along with the acceptance control charts. Like we say that R control chart and X bar control chart must be used simultaneously. And similarly, we also say that the modified control chart and acceptance control charts, these two charts must be used simultaneously. There is a specific reason for this one, and you will come to know what is that reason when I discuss the acceptance control charts. Now there are, if we just mention that there are two conditions to be satisfied. The first condition is you need to determine the upper limit as well as the lower limit of the process main in such a way that the proportion non-conforming is restricted to delta. That is the first condition you have to satisfy, and for that you need to use the modified control chart. Now the second condition that you may frequently come across, that is the proportion non-conforming which you have set as a standard, say 1%, 0.5%, is it okay? So that is the set, that is the value of delta. There is no guarantee that in an actual process at that point in time, there could be many reasons that this actual proportion non-conforming may be greater than, substantially greater than the delta which is pre-specified. So what do? Obviously, you need to use another control chart which will help you in detecting this unacceptable the proportion non-conforming this amount as quickly as possible. So initially you design the modified control chart with respect to the proportion non-conforming delta which is acceptable to you. Next, what you will do, that means if the delta changes to gamma, that means say for 1% delta is 1%. Suppose because of some reasons you are getting a value of say 3% proportion non-conforming. So whether you are able to detect this change in the proportion non-conforming as quickly as possible. So for this you need to use acceptance control charts. So I think it's clear that you know what is the specific reasons. That's why the acceptance for which the acceptance control chart is used. Now this point I have elaborated when I say that this chart is used when the proportion of non-conforming output is not restricted to specified value delta. If you remember that when we design the modified control chart, the modified control chart is designed with respect to a specified value delta. Is it okay? But because of some reason, suppose the delta is changed to some higher value, say gamma. Gamma is substantially greater than delta. So the delta is 1%, and the gamma may be 3%. Now, this chart is designed in such a way that this higher value of proportion non-conforming is detected with a probability of 1 minus beta. Beta, as you know, is the probability of making type 2 error. That means essentially probability of non-detection. Obviously 1 minus beta is probability of detection. So that is to be assured. That means a high value of probability of detection is to be assured. Is it okay? This chart is to be used jointly with the modified control chart. This point already I have elaborated. Okay. So what is the problem statement? Problem statement is very simple. We wish to detect the level of proportion non-conforming gamma with a probability of 1 minus beta. Is it okay? So with the detection probability. And make sure that whenever the proportion non-conforming becomes gamma, okay, it should be detected as quickly as possible. That means make sure that the average run length, if you recollect, we have used the term, we have defined what is ARL. That means on an average, how many sample points you are going to plot before an out of control condition is reached. Is it okay? Is detected. Now obviously, if the process has already gone out of control, so the ARL should be as minimum as possible, say 3 to 4 or say 2 to 3 sample points as quickly as possible. Whereas if suppose the process remains in control, so the ARL should be as high as possible. Is it clear? So here in this case, as you are defining the out of control condition with respect to the proportion non-conforming and with a specific value of proportion non-conforming gamma, we say that the process has gone out of control. So obviously the ARL value should be as minimum as possible. Okay. Now again we are referring to the say distribution of individual values, that is x. So again what we are showing now, that already the mu L and mu U, these two values are specified against the process mean. Is it okay? And this is the upper value, this is the lower value. Is it okay? Now this is the distribution of x, and so the corresponding value of the standard deviation, the process standard deviation is sigma, and if the proportion non-conforming becomes gamma, which is not acceptable to you, so this standardized distance is z gamma into sigma. Is it okay? So this is the distance from mu L to USL. US is already specified for the given quality characteristics, for which already you have drawn, you have been using the modified control chart. And similarly, on the other side, this is the area under the curve beyond LSL, that is gamma. Is it okay? And this is the standardized distance, that is z gamma into sigma. Okay, distance of mu L from LSL. Is it okay? So we are referring to the distribution of individual values, and we are assuming that the central limit theorem holds. That's why the distribution of x is assumed to be normal. When you refer to the distribution of the sample mean, that is x bar, that means around mu L or around mu U, obviously as per central limit theorem, so this the standard deviation will be sigma upon root n. That means sigma x bar is equals to sigma upon root n, and this we refer to the distribution of x bar. So now you have the say LCL is here and UCL is here. So even if the value is at mu L, what you find that there is an area which is within this LCL, within the UCL, this zone. So obviously this is the proportion of say this is the proportion indicative of the probability of making type 2 error. That means the process has gone out of control, but actually it is shown as in control. Is it okay? So this is the type 2 error. Similarly, when the upper value is mu U, okay, of the process mean, now the area which is within the upper control limit, that is beta. Is it okay? So again, this is when you reach at this point, so you have this area that is this indicative of probability of making type 2 error. So obviously the standardized distance from UCL to mu U is z beta into sigma upon root n, and similarly the standardized distance of LCL from mu L is z beta into sigma upon root n. Is it clear? So we are referring to distribution of the individual values x, and then we are referring to the distribution of the sample mean x bar. Is it clear? So we have defined what is USL, what is LSL, we have defined what is gamma, we have defined what is beta, we have defined what is UCL and what is LCL. Now what you try to do, that means ultimately in terms of all these parameters, okay, you need to have an expression for UCL in terms of USL, and you must have an expression of LCL in terms of LSL. That means what you are trying to do, we are trying to explore the relationship between the control limits and the specification limits. Is it okay? So and then obviously whenever you are referring to say the delta or gamma, the proportion non-conforming, so these are this proportion non-conforming is always defined with respect to, in reference to the specification limits. And so we are going one step further. That means till now we have not referred to the specification limits. Is it okay? In the control chart. Now here we are determining the control charts in such a way that the relationship between the control limits and the specification limits are explored given the problem. Another important aspect we must look into, that is the specification limit is always applicable to individual values, whereas the control limits not necessarily, excepting when you draw the control chart for the individual units, that is X control chart, and along with the X control chart, if you remember, we have the MR or moving range control chart. Is it okay? So excepting those that particular case, otherwise always we'll find that the sample size is greater than 1 and the sample is represented by its statistic, say X bar. Is it okay? So so whenever you refer to the distribution of say the process the parameter, say the process mean, that means the sample size is greater than 1. So we refer to the distribution of X bar. Is it clear? Whereas whenever you refer to the specification limit, we are referring to the distribution of X or the individual values. Now what are these set of equations? If you refer to this figure, what you will find that the mu L is equals to LSL plus Z gamma into sigma. You refer to the first figure, that means the distribution of X or the individual values. And similarly you get mu U is equals to USL minus Z gamma into sigma. Is it okay? Now we must have an expression for mu L and mu U from the second figure. That means you refer to the next figure, you will find that upper control limit is mu U minus Z beta. What is beta? Beta is the probability of making type 2 error into sigma divided by root n. What is n? N is the sample size. Similarly, LCL, you refer to the same figure, you will find that the LCL is equals to mu L plus Z beta into sigma divided by root over n. How do you get this sigma upon root n? Is basically sigma X bar, and as per the central limit theorem, you can say that sigma X bar is nothing but sigma upon root n. So this these two equations, we are referring to the distribution of individual values, whereas these two equations, for these two equations, we are referring to the distribution of X bar. Is it okay? So whenever related to the acceptance control charts, so what is the upper control limit? Is equals to upper specification limit minus this expression into, that means Z gamma plus Z beta upon root n into sigma. Is it okay? So sigma is essentially the process standard deviation. Similarly, the LCL is equals to LSL plus Z gamma plus Z beta divided by root over n into sigma. Now again, how do you determine sigma? So there could be good estimate, acceptable estimate, that is you refer to R bar control, R control chart or S control chart, and you say that the sigma, if you refer to the R control chart, is it okay? So you can have an estimate of sigma, that is sigma hat is equals to R bar by D2. And similarly, if you instead of constructing or instead of using R chart, suppose you use S chart. So similarly, so related to say the S chart, you have the value of C4 and as well as the S bar. So another the expression for sigma, that is an estimate of sigma, is say S bar divided by C4. Is it okay? So whenever you declare a process to be in control, that means we say that the first I try to control the process with respect to its variability. So if the variability is under control, then I use the control chart, another control chart, in such a way that I say that the mean or the process mean is under control. Is it okay? So so obviously, when you assume that the process is in statistical control, so in all likelihood the value of sigma, that is an estimate of sigma, is made available. Now when as we have been saying that a modified control chart must be used along with the acceptance control chart. So when the principles of both the charts are applicable simultaneously, getting my point? So in the first case, we know that what is the mu u, what is the value of mu l. We know what is the distribution of x. We also know what is the distribution of x bar. We know, given the quality characteristics USN and LSN, and then we say that the given control chart, there is a probability of making type 1 error. Is it okay? And then there is a probability of making type 2 error when the proportion non-conforming changes say any value from say the delta. Is it okay? So so then we say that under these 4 or say 6 conditions or 4 or 5 conditions, you have to meet all these conditions simultaneously. So obviously the modified control chart must be used along with the acceptance control chart. So that is the norm. So under in this context, we say the principles of both the charts are applicable simultaneously. Is it clear? I think it is clear. And sample n, sample size is given by this one. Is it clear? That means what you try to do, that means UCL for the acceptance control chart, the expression for UCL is equated with the expression for UCL for the modified control chart. Is it okay? So either you equate both these expressions and get the expressions for n, is it okay, sample size, or you can say that I will equate LCL expression of acceptance control charts with the LCL expressions for the modified control chart. So again you will be getting an expression for n. So what is the expression for the sample size? When you combine both these charts, that is Z alpha plus Z beta divided by, this is Z1, this is not Z alpha but Z beta, there is some problem. So this is Z alpha plus Z beta into, say, you have Z delta, Z gamma minus Z delta. So it is Z delta, Z gamma minus Z delta. It's clear? Okay, so we'll make these changes later on. Okay. Now, so this is the special purpose. Say we are discussing the special purpose control chart, right? Now, as I have already told you, there are varieties of special purpose control charts. Okay, So the three specific control charts we have used till now. First one is the regression control chart or the trend control chart. That is the first one. The second one that we have discussed, that is the modified control chart, and the third one is the acceptance control charts. Now the next important control chart we are going to use, that is the cumulative sum or Cusum control chart. Is it okay? Now I will before I discuss in detail this cumulative sub control chart, let me highlight some of the important points, okay, related to control charting. As you are aware that the basic theory behind control charting was introduced many years back in 1920s by Walter A. Shewhart. So that's why many of these control charts are named after him, and they are referred to as the Shewhart control chart. So the Shewhart control charts are very less sensitive to small shifts in the process. This small shift may be in the order of 1 to 1.5 sigma or less. Is it okay? It's not 1.12, it is 1.5 sigma or less. Is it okay? That means when the sigma of the process is known, that is the first exercise you carry out before you start using a control chart. That means given a quality characteristics, given a process, is it okay? And it's a running process. So you must know with respect to the quality characteristics what is the value of sigma. And this sigma with respect to the quality characteristics may be referred to as the process standard deviation, an estimate of the process standard deviation. Now, what we are trying to do, that means we are using control chart, that is the first objective. To what extent we are able to control the variability. So the variability, that means the sigma, that is also a random variable. So, and so if the process mean changes, suppose we need to control the process mean. So the change in the process mean, that means the shift magnitude, many a time it is expressed in terms of sigma. That means what we are assuming, that in a given process both mu and sigma may change, and they're essentially they're changing simultaneously. Okay, now we need to define the small shift as well as the large shift. Is it okay? Large shifts are basically more than 1.5 sigma, that is the norms, or say more than 2 sigma. Is it okay? That is the norms. So what the researchers have found, that the Shewhart control chart is very, very sensitive to a small to a large shift. Is it okay? Whereas it may not be that sensitive, okay, when the shift magnitude is very, very small. That means less than 1.5 sigma. In many sophisticated processes, providing high quality products with very intricate shapes and very tight tolerances, like say automobile parts or the aircraft parts. Is it okay? So small shift in the process may make the process out of control. Is it okay? So if there is a small shift in the process parameter in the process, I mean the process parameters, you say that the process has gone out of control, because very tight tolerances you may not be able to achieve. So the control chart is a special purpose control charts need to be designed under such a case. That means you design the control chart, you redesign the control chart, existing control chart in such a way that even the small shift in the process parameter value can be detected quickly. Okay, so A control chart needs to be designed in such a way that the small shifts can be detected as quickly as possible. Okay, so the Cusum control chart is designed and used to meet this purpose. Is it okay? Now, so this is a very special purpose control chart, and I will just explain. Okay, what are the steps to be followed? Okay, and what is the rationale behind following these steps? Okay, in developing a Cusum control chart. Is it okay? Now, what do you try to do in the previous in previous cases, like when you use the Shewhart control charts? What do you assume? That all the samples, okay, they are independent with one another. That means the sample values are not dependent. Is it okay? And at any point in time, at a particular when you draw a sample, and at a particular point in time, you are you are using a sample statistic, and you plot the value of that sample statistic. Is it okay? That means the value you plot is indicative of a condition at that point in time, or that during that period of time. Is it okay? It has got no relationship with the previous conditions. Getting my point? So now what we are trying to do, that means we try to incorporate all the information in the sequence of sample values by plotting the cumulative sum of the deviations of the sample values from a target value. That means here is a process I have designed. Now, with respect to the process parameter, okay, given process parameter, I must know what is its target value. Now, the actual value when you get at a particular sample, so you know that what is the deviation from the actual value. So that is a particular sample. What you need to do when you arrive at a particular sample, now you need to consider for all the previous samples the deviations from the targets, and you have to add them together at a particular point in time. So the Cusum charts incorporates all the information in the sequence of sample values. That means the time order is to be maintained. That I have already told you, that when you construct a control chart, make sure that the samples are drawn, okay, as per the time sequence by plotting the cumulative sum of the deviations of the sample values from a target value. That means at a particular sample, okay, so when I define the deviation, now this deviation incorporates all the deviations, okay, that have already occurred in the previous samples. Is it okay? From the first sample. So just I'll explain it. Means how do you arrive at this cumulative value? Let xj bar be the average value of the jth sample with n equals to n greater than 1. So this is the average value, not values. Okay. So just one value. That means you have n number of values in a particular sample, jth sample. You compute the average value. Mu0 be the target for the process mean, as already mentioned. Now, how do you compute the Cusum? So the Cusum at the ith sample. That means how do you arrive at the ith sample? That means you have started from the first sample, second sample, third sample. Like this, you proceed, and ultimately you reach the ith sample. Is it clear? So the I could be 1, I could be 2, I could be 3. Is it okay? So I is a variable. So at the ith sample, how do you compute the cumulative the sum? That is from j equals to 1 to I up to I, including I, you compute the xj bar minus mu0. That means j equals to 1 to I. Is it okay? That means up to I, including I point. Sum up to and including the ith sample. Is it clear? I think it's clear. When this is your the cumulative sum of the deviations, sum of the deviations from the target value up to the ith sample point and including the ith sample. Is it okay? So the Cusum chart is very effective when n equals to 1, as when you will be referring to the control chart for the individual units, that means X chart. Okay, you know what are the, or under which conditions you have no other alternative but to go for, using X chart. Is it okay? So the sample size is very, very less. Okay, so it is 1. So in many cases you'll find if you deal with say the process industries, is it okay? The case of n equals to 1 is very, very common. So in this case, the average sample value changes to the individual value. That means there will be just xj, not xj bar. Is it okay? So this cumulative sum control chart may be recommended to be used for say the process industries, and whenever say is a chemical plant or the chemical industries, okay, as an example. So you will find that you need to assume that n equals to 1. Is it okay? And then accordingly you define the cumulative sum. Is it okay? So the first thing you have to do, that is the cumulative say the sum you have to define with respect to the given the process parameter. Is it okay? And for which target value is to be specified. Now just what I am telling you, certain decision rules, let me just highlight, and then in the next sessions I will be discussing the other aspects of Cusum chart. So what is the decision rules that is to be known? That is, if the process remains at mu0, that means an in control state, that is the target value, Ci has random fluctuations with mean at 0. Always, the xi values there will be randomness. That means there is randomness only when the process is in control. So obviously the mean at 0. Is it okay? If the process mean shifts upward to say mu1, which is greater than mu0, substantially greater than mu0, Ci shows an upward positive drift. And similarly, if the process mean shifts downward to mu2, which is substantially less than mu0, Ci shows a downward or negative drift. Is it okay? A methodology or a scheme is to be developed so that from the trend pattern of Ci as being observed, we may be able to conclude that there is a significant change in the process mean, determine the changed value of the process mean. Is it okay? That you have to do, and identify the sample where the change in the process mean taking place due to assignable causes. That means at what point in time for which sample the process has gone out of control. So that particular the sample you have to detect, and you refer back to that particular sample. Is it okay? And you just check the process conditions and whether you are able to identify the assignable causes related to out of control conditions. Now here, whenever you talk about Cusum control charts, the researchers have developed two approaches. Is it okay? In fact, there could be other approaches, but these two approaches are always referred to, so you must be aware of. In fact, on the Cusum chart, there is lots of research going on. Is it okay? So, from the imperfect the systems, we may be going to a perfect system. Is it okay? But the two important schemes, they refer to the scheme or the approach for the Cusum control chart. We must be discussing, and that is, first one is the tabular or algorithmic Cusum. This is the scheme we need to use, and the next one is the VMask template. So in the next sessions, I am going to discuss these two schemes. Okay.